Chapter 7.1 Part 2. In Part 1 we had the introduction to electric fields and we had uniform electric fields. Now we will see something more here, and then the next part you will have the radial electric fields. Okay, that is 7.1 Part 3. By the end of this section you should be able to describe the experimental setup which Robert Millikan used to determine the charge on an electron. So you see how he determined the charge on an electron, the experimental setup he used. So Millikan's oil drop experiment explained how different areas of physics can be brought together in one experiment to solve a problem. See, this is not required by the specification, but they are explaining this so that the content in this section has been included to illustrate how different areas of physics can be brought together in one experiment to solve a problem. In experiment to determine the nature of fundamental particles, scientists can use mass spectrometer. Okay, so for more details you can go through this. I think for chemistry, those who are taking chemistry would learn about the mass spectrometer in detail to find the ratio of charge to mass for particles. This is a fundamental property of a charged particle and identifies it uniquely, but until the determination of the value of the charge on an electron, it was impossible to break down the ratio and find the mass of that particle. So what happened in 1909, Robert Millikan developed an experiment which determined the charge on a single electron. Although Millikan had a variety of extra bits and pieces to make his experimental function successfully, the basic essence of the experiment is very simple. A charged oil drop had its weight balanced by the force from a uniform electric field. He also undertook a variation in which there is no field and the terminal velocity is determined. Now see, two things. So if the upward force due to the, now see, this is an electron, so the electron, let's say we have electron here, when it is falling this way, now this is negatively charged, so that will repel the electron. So if you can have a situation where the upward force, the electric force, balances the weight, then if you know the electric force and if you know the mass of the electron, you can find the charge of the electron. So if the upward force, which is the force due to the electric field or the electric force, see, if it's an electron here, it's negatively charged, so this is also negative, this is positive, so the force on that electron will be upwards, the electric force, the weight will be downwards. So if you can bring it to a point where the two forces are balanced, the electric force and the weight force, then we can say we can find the electric force. If we know the electric force, okay, from the V and this, we can see what is the electric force. We know D, we know V, then we can find F, because E equals V over D and also equals F over Q. So if we know the charge and if you know the force or if you know the mass, then you can find the charge. So we will see how it's done. So that is one way. See, a charged oil drop had its weight balanced by the force on a uniform electric field. He also undertook a variation in which there is no field and the terminal velocity is measured. So also we can say, yeah, we can find it that way as well. It will reach terminal velocity. This will be some unknown multiple of the charge on an electron. So we don't have electron here, we have this oil droplets. So if it has, say, n number of electrons, then the charge, total negative charge will be the n number of electrons times the charge on an electron. Okay, so it should be n times the number of electrons times that which is the charge on an electron. That's what is meant by this. Yeah. And then one in which the field provides he undertook way in which there is no field and the terminal velocity is measured, and then one in which the field provides a stronger force than gravity and the terminal velocity upwards is measured. Okay, so it's moving upwards, not downwards. See, you increase the force, electric force, so much stronger, it's stronger than the weight, stronger force than, it should be gravitational force, and then it will move upwards, so then it will reach another terminal. Okay, So when the oil is squirted into the upper chamber from the vaporizer, friction gives the droplets an electrostatic charge, because when it moves like this, it rubs against the air, and then it will get charged. This will be some unknown multiple of the charge on an electron. So here we have the net charge. Okay, so then from that only we determine, not the total number of electrons that is on the oil drop. Okay, so some electrons may be removed when it is going through the air, when it gets rubbed against air, or we can also say the electrons are added to this. Okay, so here what's happening is, we can say the electrons are added by the air molecules rubbing on the oil drops. Electrons are transferred from the air molecules to the oil drop. So now there are additional electrons, so more negative charges than positive charges, so there will be a net negative charge. Because electrons have been added or removed due to friction, as the drops fall under gravity, some will go through the anode and enter the uniform electric field created between the charged plates. If the field is switched off, they will continue to fall at their terminal velocity. Okay, so here is the setup: vaporizer, anode, cathode, viewing microscope, charged oil droplets, variable PD, light source. Schematic of Millikan's oil drop chamber. Now you have learnt Stokes law in the AS lessons. Under mechanics, you learn this. Sir George Gabriel Stokes investigate fluid dynamics and derived an equation for the viscous drag F on a small sphere moving through a fluid at low speeds, where r is the radius of the sphere, v is the velocity of the sphere, and eta, this is a Greek letter, is the coefficient of viscosity of the fluid. For Millikan's oil drops, the density of air in the chamber is so low that its upthrust is generally insignificant. Okay, so less air particles we can, so density of air is low, although it would have to be considered if we wanted to do really accurate calculations. Under terminal velocity, the weight equals the viscous drag force. So this is say when it is falling. Okay, when it is falling, the weight force will equal the viscous drag force, which we call the Stokes force. Now remember, this Stokes force applies for a small spherical object moving at slow speeds. Okay, so remember, when you learn Stokes law, you can't apply this equation for anything. It applies for a small sphere moving through a fluid at low speeds. For that only this equation will apply. You can't apply it to large things. So it has to be spherical. It has to be moving through a fluid at low speeds. So remember that, you have learned it in the AS class, because some exam papers they ask you regarding this, especially in the AS lessons. Then we have this, so the weight is equal to the viscous drag or Stokes force, and n is the viscosity of that fluid, and in this case it is air. R is the radius of the oil drop. When held stationary by switching on the electric field and adjusting the potential V until the oil drop stands still. So what happens? So initially it is falling like this with terminal velocity, then we increase this so much, the potential difference here, that the electric force will be upwards and it comes to a stop. Okay, so it will fall, decelerate and come to a stop. So in the beginning it will be falling with terminal velocity when, let's say, when this electric field is not there, when this is switched off. So it will fall, and then the weight, which is downwards, will be equal to the viscous drag or Stokes force when it has reached terminal velocity. Then you switch this on, let's say, then what will happen? It will be such that the force is upwards. So the force will be upwards, the electric force, and that will cause this to decelerate, and you keep increasing this until it comes to a point where it stops. So when it stops, we can say, and it's stationary, then what happens? The upward force, the electric force, is equal to the weight now. Earlier it was the viscous drag. Now since it is stationary, there will be no viscous drag, it's not moving. So what is keeping it stationary is that the upward electric force is equal to the weight. I think you can see this. Okay, so if you want, you can sketch a diagram also. Okay, maybe I can even draw it so that it becomes easier for you to understand. Okay, so in the beginning, when it is falling with terminal velocity, so let's say this is the oil drop, then when this is when it is moving. Okay, so here it has a velocity downwards, so here we have the viscous drag or Stokes force, I will call it D, equal to the weight. Now in the second scenario, second case, what you will have is again the weight, it's not changing, that is the same W, but now it is stationary. Okay, so here V is equal to 0, and what balances that is the electric force. Let's call it EF or FV. F for force, E for electric. Okay, so this is what we have. Now here this is the weight, here the resultant force is 0, that's why it's moving with terminal velocity. Here also the resultant force is 0, and that's why it is stationary. Remember Newton's first law. Okay, so an object should be moving with uniform velocity or it should be stationary if the resultant force is 0. I mean, Newton's first law is actually saying if that object is stationary, it will remain stationary. If the object is moving with constant velocity, it will move with constant velocity unless an external force acts on it, which means the resultant force on the object is 0 when it is either this case or this case. Okay, when it is stationary or when it is moving with constant velocity. So here in both cases the acceleration is 0. If the acceleration is 0, that means the resultant force should be 0, because it is the resultant force which produces an acceleration. Okay, so that's why they set this equal to this. Now this is the first case. If I show you the diagram, see, this is the Stokes force, that is equal to the mg, weight. See, that is what we have here. Okay, then the second case, see, this is the Stokes force. You have learned it in the AS class. If you are not familiar with this, you have reviewed that. Stokes force, again briefly it's explained here. When held stationary by switching on the electric field and adjusting the potential V until the oil drop stands still, so then the weight is equal to the electric force. So this is the electric force, that is the weight. Then we have this. So now we know that this is the electric force, this is the weight, and this, you know, E is equal to V over D. Remember we learned it earlier in the previous video. Okay, remember the definition of electric field strength. There we learned two equations. One is equals F over Q, the other is equals V over D. Then we can make Q the subject of the equation to find the charge. Millikan could not measure R directly, so he had to eliminate it from the equations, because, you know, that is, R is the radius of the oil drop. Further development of Stokes' law tells us that a small drop falling at a low terminal velocity will follow the equation. Now again, you learned this in the AS class when you learned about Stokes' law. Okay, so this is the density of the oil, this is the density. Again, if you are not familiar how to get this, you have to review that lesson. I would have uploaded a video on that lesson. You can see the Stokes' law, Stokes force, which if we again ignore the low density of air, rearranges to this. Now density of this is, let's say, low, so we can make it 0, air. Then we get this equation when we make R the subject of the equation. This thing goes up there, V is there, this is 0, then you have 2 and 2g that down here, and take square root. Then we have Q, the charge will be, remember this equation here, so 6 pi this thing. Okay, we then times R, so we can keep the R out there, and R is equal to that. Then you get this simple mathematics. Millikan did the experiment several hundred times, including repeated measurements on each drop over and over again, letting it fall, halting it with an electric field, and then lifting it up again with a stronger field before letting it fall again. From this data, he found that the charge on the droplets were always a multiple of this. So you see, approximately it's the charge on an electron. See, this is the charge, actual, this is the charge, then he got a very close to that, which is less than 1% away from the currently accepted value of the charge on an electron. For this and work on the photoelectric effect, Millikan was awarded the 1923 Nobel Prize for Physics. Okay, so that's the end of that subchapter, chapter 7.1 part 2, which was about the Millikan's oil drop experiment. Now make sure you answer all these questions here and check the answers to these questions in the answers sheet. The questions here are based on what you learned here. Now in the next lesson we will learn about radial electric fields, which is chapter 7.1 part 3.